Let's talk about rationalizing substitutions. So when we make a rationalizing substitution, this is what we're doing. We're basically turning non-rational functions into rational functions by using a substitution. Okay. In particular, we can integrate integrals involving radicals by making substitutions that look like this. Let's say you have u equal to something like the nth root of some f of x. So let me show you a quick example, I suppose. Let's say that you have your u is equal to the cube root of x plus 9. After you made that substitution, you would be able to cube both sides. So you'd have like u cubed is equal to x plus 9. This would allow you to solve for x. This would mean that x was equal to u cubed minus 9, for example. And you could also solve for dx by differentiating. So this would mean that you'd have your dx would be equal to 3u squared du. So you can totally, make substitutions using these rationalizing substitutions. All right. So let's take a look at a very particular example. Let's look at this example right here. All right. I look at this function. It's not a rational function right now because the numerator has a radical in there. Because this is just x and doesn't have an x squared, I'm not going to use trig sub on this. Based off of experience, I realized that this is going to be a rationalizing substitution. So what I'm going to do is I'm going to let u be equal to the square root of x plus 9. Okay? And then just as I did to the right over there, I'm going to square both sides. So this means that u squared is equal to x plus 9. And if I wanted to, I could solve for x. I could get x is equal to u squared minus 9. Okay. Now let me differentiate both sides. Differentiate left-hand side, you get dx. Differentiating the right-hand side, you're going to get 2u du. And once I have those, I can make my substitution. So the numerator is just going to become u. So we're going to have the integral of u. The denominator was originally x, but now that's going to be a u squared minus 9. And I have to tack on the dx at the end. So in this case, the dx is equal to 2u du, like this. Okay? So we can take this 2, move it outside the integral because it's 2 times the whole integrand. So when I do that, I'll have a 2 out in front. I have 2 powers of u being multiplied together. That gives me a u squared over u squared minus 9 du. Okay. Now that I look at this guy, let's make some comments here. This original guy was not rational because of the radical, but this one now, this is rational. You have a polynomial divided by a polynomial. So I'm unclear if I should just leave it at this point. I suppose I'll continue it on until we can figure out which case we're in. So look, I have the degree of the numerator is 2, the degree of the denominator is 2. That means that I'm going to need to divide. So I'm going to take u squared divided by u squared minus 9. So I'm going to have a 1 in my quotient. I'll have a u squared minus 9. And when I subtract these guys, I'm going to get 9 coming down. So really, this integral is going to become 2 times the integral of 1 plus 9 over u squared minus 9 du, right? So I guess at the next step, I would factor the denominator. So this could be 2 times the integral of 1 du plus 2 times the integral of, well, let me factor out a 9 from the second integral. So I'll have a 18 times the integral of 1 over u squared minus 9 du, like this. And this is going to give me a 2u. This part is going to be plus 18. And then I can factor this guy. The denominator factors as u plus 3 and u minus 3 du. And then, you know, this is the distinct linear factor case. So this is case 1. Okay. So, you know, you're going to continue your integral in that way. I think I'll just leave it here so this video doesn't go on too long. But this is basically left with a case 1 integral. So to summarize, we've taken a function that was not rational. We made a rationalizing substitution, and the result was a rational function, and then we can just do partial fraction decomposition on that. All right, everybody, take care.